So a function passes the vertical line test if you graph it. You put random straight lines through it, it will only touch it once. If you do horizontal lines and it only touches one time on your graph, then it's one-to-one. So a function so a graph could be a function but not one-to-one, or it could be both. But it has to be a function before you talk about one-to-one. Okay. Let me give you an example of which one that is not one-to-one down here. Let's say 1 goes to 6. 2 goes to 7. 3 also goes to 7. So this is where it fails the one-to-one definition. 4 goes to 5. Oops, I put 5 twice. Let's erase that guy. I'll just put a 0, make it up. Doesn't matter. So this is not one-to-one. Okay. Give you a visual in just a moment. A graph, actual function. I told you can't draw, man. All right. So we all agree that a parabola is a function, right? If you draw vertical lines through it, it passes the definition. You just imagine, or if you want to draw it, you can. Just draw vertical lines through it. It will never hit more than once. But if you draw a horizontal sideways line, it's going to hit 2 times. So if it hits twice, it is not one-to-one, because do you agree that 2 goes to 4? -2 also goes to 4, right? So you have 2 different values going to the same place. So that violates one-to-one. Does that make sense? What one-to-one means? Every single X and Y have a unique pair, right? Unique partners, I guess. This guy, would you say this one right here looks like it is one-to-one, right? If you draw horizontal lines, it's not going to hit more than once. Same with square root x. If you draw vertical lines, it'll only hit 1 time, and horizontal, it'll only hit once. So this is a one-to-one function. Okay, so is the cubic. That's how you can tell. You can also check the definition we wrote down, but the easiest way is to graph it and just look at it. Okay. Are there any questions about that? That makes sense? Any question on what is one-to-one? That's what I'm trying to show you here. These domain values must only have must have a unique pairing. Okay. Over here, see how they all went to their own different place? So we're good. 2 and 3 went to the same place, so we were not good. Okay, so the homework. Let's do some homework problems. I don't think we need any more definitions, but let me check. I'm gonna give you one more note. So if function is 1-to-1, if every horizontal line intersects the graph of the function at most once. That's what we showed just now with the graphs, okay? Is the following 1-to-1. What do you think about A? Is it 1-to-1? No, right? If I draw a horizontal line, I'll probably hit at least 2, maybe at most 3 places, right? So no, not 1-to-1. I'm going to shorten 1-to-1 by 1-1. Well, part B. What do you think? Yeah, it is, right? Part C. That's part C of function. It is, right? Passes the vertical line test. So now, so always ask yourself first, is it a function? Now ask yourself, is it 1-to-1? No. No. It fails a horizontal, right? What about D? No, right? Do we see why? It's not a function, so why are we talking about 1-to-1, right? So always check. It's not a function. All right. We'll move to, let's look at the homework in just a moment. Right. We're going to shift to the homework. Sure, it comes out here. All right, so this is the homework 4.1. Can you guys see this? That's too small.
Yeah.
All right, that better?
Yeah. More.
Well, you don't have to read the paragraph. Can you see the chart?
A little bit, yeah.
So is this chart, if we consider this chart a function, is it one-to-one? Right.
Yes.
You see anything repeat?
Oh, yeah.
So since you have two cities assigned to the same value, it's not one-to-one, right? That makes sense. So you're trying to find something that repeats, because they should all have distinct values. Okay. We can
It's not.
pretty much for one-to-one, yeah. Just check that every single input has a unique output. That's the definition. Okay, let's look at another one. I don't think we don't have to really write this down. I just want you to remember the concept. Here's your graph function. Is it one-to-one? They're telling us it's a function, so don't have to worry about that. Yes or no? So no, okay. C is a C. No, there's a horizontal line intersects a graph at more than one point. D. Oh. Each x y corresponds to every y value. I think C makes sense. C. About this one, we don't have the graph, but you could graph it yourself, or remember what kind of function that is, the parent function. What type of graph is this? I just put it in there. Should be towards the bottom where, right after test 4, or in the test 5 area. Yeah. Got it?
Yeah.
Okay. Yeah, this is all test 5 material. This is the beginning of test 5. So what type of graph is this? Yeah, it's just a line. It has slope, so it has a slant to it. All lines are one-to-one unless they are, unless they don't have a slope. If it's vertical or horizontal lines, then no. But any other line that's not that, then you're good. So what you could do in this homework question, just graph it and look at it, okay? Well, look at the parent and remember, okay, well, what shape is it? And that shape should be similar. So the cubic has that S shape, right? So either graph it in your grapher online, I don't really care. Or look at the parent. What was the question? I forgot. 6q minus 1. Repeat. Yeah, you'll have the same, you have two different, they'll all have unique values. Oh, no, I just like. Gotcha. Anyway, it's straightforward, right? No issues with 4.1 so far? What's expected? Okay, so it's pretty much it. Let's see. Let me see if anything interesting comes out later. Oh, here we go. 5 and 6. 6. So after 5, they start talking about inverses. So we need to define that first. Inverse function. So let f be 1-to-1, a 1-to-1 function. Then G is the inverse function of f. If you compose them with each other, they cancel out and leave you with just an x, then it's an inverse. This must be true for every x in the domain of G. Also the other direction, G of f must also cancel out for every x in the domain of f. So that's one way to show that a two functions are inverse of each other. So if I give you a function and ask you, okay, are these two inverses of each other? You would compose them in both directions and they cancel out. You have proven they are inverses, okay? Also, the reason we care about inverses is because it can undo whatever a function does. It'll send you back to the original input. Okay, so if you have a fancy function that you want to know where it started or what it did, you would use the inverse on it. Okay. Also, inverses can be used for solutions. Technically two, I guess. All right, prove F and G are inverses of each other. You're going to compose them together and see if they cancel. That's it. So I'm 90% sure you'll have a test question like this. So just compose them. Also, if they are inverses, then the domain of one of them will be the range of the other, and the range of the other one will be the domain of the other one. So if you have F, domain of F will become the range of its inverse. That makes sense. Okay. So all you got to do is compose them. So F of G, which means F of cube root of x plus 1. So plug that into here. That makes sense? So G is going inside the F. So you put it into this specific X here. Once it's in there, do you see that the cube and cube root will cancel? Right, they're opposite fractions. So you'll end up with just this. And then x plus 1 minus 1 is just an x. That's what we want to see. Just an x. Once you get the x, then we've shown in one direction that it's true. But for inverses, we got to do a proof that's what's it called? It's a double implication proof. So in logic, if it's true both directions, you have to prove one way, and then you got to prove you can go back. Okay, if it's not bidirectional, then you just show that it goes A to B. But here we're showing it goes A to B and then B to A. Okay. But anyway, I'm not gonna lecture you on logic as much as fun as that would be. G of F, do the other direction, so it has to be true. Otherwise, they are not. So if it fails in one direction, then we just stop. So plug in the x cubed minus 1 into G. So I'm putting parentheses so you can see that it was plugged in. They don't actually do anything. Okay. So at this point, you see what's going to happen. Anyway, any question on the algebra here? Is it okay? On the algebra, is it, you see what cancels and what the composite was? Composition? Yeah, let's go from the top. So we got F and G. The formulas or the definition up here says, if you compose them both directions and you get an X, then they are truly inverse of each other. So I'm trying to prove that they are inverses. So I did F of G, put the G inside the F. So there it is. F, all it does is cube whatever you plug in, right? And then subtract 1. So it's cubing my input. The cube cancels the root, subtract 1 cancels that 1. We got an X. The other direction, input F, I'm plugging in x cubed minus 1 into this specific X there. So there it is. X cubed minus 1 plus 1, those ones are going to cancel. Cube root of a cube is X. So we've shown that, yeah, it's true. Okay. One last definition, we'll focus on examples. You guys ever take that? I don't know if they still do it, the prep class in high school? You guys know what I'm talking about? No. Or you take a class in logic and they do different math stuff with you. I think different colleges come and present that to high school students. It's a pretty big program. Logic, well, for sure they cover logic tables like P's and Q's, prove that this table is true using and or statements. Do you remember that? Here they still did it. It's very useful for arguments. A lot of the old school mathematicians were attorneys full time. They did math on the side. There's a yeah, way back when, yeah, like a few hundred years ago. They had because they had to construct a logical argument. Because if it's built off logic, you can't, right. So once it's strong and built, you can't really do anything, especially when you write contracts. If you write them a certain way, you agree to it, then, you're trying to make sure there's no holes so they can't get out of it.
Okay.
But yeah, all legal arguments are based off logic. But so are all math definitions and formulas and properties. Logic is necessary. That sounds weird. The definition of inverse functions. The domain of f is the range of f inverse. And the range of f is the domain of f inverse. So they basically switch. That makes sense. So if your regular function has domains x, range y, then the inverse will be swapped. Domain y, range x. That makes sense. That's what that statement is saying. You just swap them. Which makes sense because the inverse brings you back to where you started. So you put an input and it gives you you put an input in the domain of the inverse. Yeah, so if you plug in a range value into the inverse, then you would get the domain of the original. You would just undo it. Okay.
So the second one's supposed to be the one for the last step.
So by definition of inverse functions, the domain of f is the range of f inverse, and the range of f is the domain of f inverse. F to the -1.
Oh, for the second, because the only first one it's -1, then -1.
Yeah, this little -1 right here, that means inverse.
Oh,
Yeah, in the book, that notation is inverse. It's not power -1, it's specifically saved for inverse function. So if you see that on an F, that's what they mean. Okay. Let me give you a picture. Open the book. I'll put it back in a second. Here. So if your x is the domain and y is the range, right? F will take any input over here and change it into an output in the range set here. The domain will send these values back. That's all that paragraph was saying. Okay, just sends them back. All right. So look at this homework question. Knowing that fact, are these inverses of each other? Right, the domain and ranges have to swap. Do they swap here? Looks like it, right?
Yes.
So yeah, so F and G are inverses. For this specific example. Okay, does everyone see why? Okay. Let's do this one on paper. So I'm just gonna call that set of values or points. F. Bring that back over here. And we'll take a break in just a moment. So they told us this is 1-to-1, and you can see it. So the inverse of this would just be swapping the points, because the definition tells you all the inputs become outputs, all the outputs become inputs. That's what the inverse does. So F inverse would just be 7, -3, 5, 3, 9, 4, based off that definition. Excuse me. That makes sense. Yeah, that's all. But this, all it is just conceptual. There's nothing really to do. So if I give you a graph though. Oh, wait a sec. Yeah. Look at number 8. So here's the function of some 1-to-1 function, F, I guess. If you just swap all the X and Y points, what would the graph look like? Which one would it be? Yeah, I think you're right. Let's see. Oh, don't change. Do you see why? Yeah, it will be,
Representing the one that would be the picture.
yeah, so this is the red one's like your F. And we're swapping all the, so all the X points, all X, Y points on here. You're gonna put. So if they're reflected over that Y goes X, Y. Okay, so if you grab a few of them and just swap them, you'll end up with this shape.
Okay, I would like, that I was only showing the right for them.
Yeah, you can barely see it, right? For part A, or answer A. Okay, that's pretty much it for 4-1. Let's take a,
Material for S5, right?
yes, let's take a small break. It's 4. Go to page 157 in your workbook. Do the first 6. You want, we'll start up again in about 10 minutes, 15 minutes.
What page is it?
158. And then we'll start 4.2 whenever your break's done. So in this section, we'll talk about defining exponential functions. So we got to be comfortable with our exponent properties, okay? So here are the properties. For any real number, a greater than 0, and a not equal to 1, the following holds. A to the x is a unique real number for all x. B, a to the b is equal to a to the c if and only if b is equal to c. So this can go both directions, okay? Whenever when you see a math statement that says if and only if, that's a double implication arrow, okay? So if this is true, then that is true. If this is true, then that is true. That's what I mean, okay? The difference being up here, right? If this is true, then something else is true. That's a single direction. Like this guy right here is one direction. If a is greater than 1 and m is less than n, then a to the m is less than a to the n. You see what I mean by single direction versus double directions? Like this type of argument, right? If this is true, then this is true. If this, then that. Over here is if this is true, then this is true, or the other direction. If B equals C, then this is also true. Whenever you're having an argument with someone, you can't. If you can't, make the assumption, right? If this is true, then that is true. if A implies B, B does not necessarily imply A. A lot of people make that assumption, and that's why a lot of people are wrong when they're arguing. Also, if anyone uses an absolute in an argument, they're automatically wrong. Whenever you use the word always or never, you're just wrong automatically. Just need one example that shows I did it once. So, but absolutes are never true. No, shouldn't. But if you start arguing with too often, people might get annoyed. So, you know. I've learned you should always pick your battles. As fun as arguing is.
Yes, it's.
Yeah. Arguments are just logical puzzles.
Mhm.
Let me give you the definition of a exponential function. If A is greater than 0 and A is not equal to 1, then the exponential function with base A is this guy. So the homework itself is not difficult, but I just need to make sure you have the definitions before we start. What's bothering you, Kimberly?
Mhm.
Which one?
Yeah. Like zoom in.
Let me see if I can a little bit. To zoom. You're on part A, right?
Yeah.
Okay. That better? Yeah. Yeah, there's some cool research where they can reset the genes in your eye so they turn back to when you were a teenager. And it's a new type of research. They're resetting the genes in your eyes so you can have young people's eyes forever. Until you die, I guess.
So when is that?
It'll probably be out when we're old,
What?
but
My eyes.
no, you have the same eye. We just reset the genes so it just goes back to how it was when you're like 18, 20. And
What if you were to have like leasing, is that when it's inverted back to being one?
I don't know, honestly, that's a good question. Not sure. Cause like, that's like, 'cause they've already changed the eye. So I think it would probably redo the muscle itself and the blood vessels and the veins, but it'll still be the same shape. So I think it would probably be better. Because I know when you hit 40s or 50s, your eyes lose that ability to focus. So they start having issues looking at things close by or, up close. If you ever see older people doing this, right? Yeah. They lost that, muscle flexing.
The actual what's strengthen like ability of getting that like that, like visual preference.
Right.
Oh,
Right.
okay.
So it's
Okay.
it's like you have brand new eyes because the eye itself doesn't regenerate. One of the few parts of the body that doesn't, continuously regenerate.
It's even with like teeth, I think even when you're baby, you have like very good teeth, like all the way back, like the slow.
Yeah.
We're going to see like baby extras and have like giant like rows of teeth.
Yeah, that's true. It's kind of creepy when you see them. But they're doing some cool research for anti-aging. So they're wondering if they can apply it to like joints, muscles, or eventually the entire person.
But that could essentially be
Umbilical cord,
It's
that's how they're.
what's that?
Stem cells. And regenerate.
Yeah, I mean that's a whole nother field of research. Is pretty cool too. They're doing a lot of interesting things. Yeah, one of my buddies did they injected stem cells that they got from his stomach into his joints and they regenerated his cartilage. So he can run around again like he was a young man. He's already in his 70s, but now he's good. That's not the one. Oh, here it is. So look at the homework. It's pretty chill. We already talked about this. Anything to the 0 power is going to be 1. No matter what it is, it will be 1, except 0. So there's nothing really to do here. I want you to get comfortable plugging in numbers into the power. So here, if there's parentheses, then that means zeros on the entire thing. So it'd just be a 1. It's just the definition. Anything to the 0 except 0 will always be 1. Now, if the negative was outside, it would be -1. Because if the 0 would only be applied to what's on the parentheses. It's like this guy. See how there's no parentheses? So it's assumed the 0 is only on the 6. So the answer would be -1. So the 0 changes the 6 into a 1, but that minus is waiting for you. Okay, 8 to -2. We've kind of talked about this stuff already, but do some on the paper. So if you see it like written this way, right? This becomes a 1, but then you have a minus. If you see it written this way, they mean this. So same thing. So these two are the same. Okay. If it's inside, then who cares? Everything to the zero. A to the negative 2, you have to remember the properties of exponents. So remember I sent you a sheet with all the properties? So in this chapter, you should probably have those ready. Remember we said if you have a negative power, you could bring it to the bottom and then apply the power. So you cross the sign, or cross the line, and then you change the sign of your power. That's it. We also said that if you have a fraction with a negative power, that it would flip. Oops. Then you would apply the power on each part, the numerator and the denominator. But once you flip it, it changes to positive. So 6 times 6 times 6, what is that? I don't know. 16, sounds right. As you can see, the beginning of the homework is pretty basic. Talked about this already. So let's move on. The second half of the homework wants you to be comfortable with notation. And I'll wait up right here. All right. So f of 3, that means you plug in a 3 wherever you have an x. So just multiply it 3 times, right? That's it. So the second half of the homework is just plugging numbers. Nothing crazy. There'll be some that will ask you to graph them. So make sure you know what a exponential looks like. The parent function, so it's on there. The parent function that I gave you. Then they'll ask you to solve equations, exponential types. Okay. So solve for x. If you can make them the same base, we can use that property we wrote down at the beginning. Remember, we said that it was two directions. If a to the b is equal to a to the c, then the double implication means that b is equal to c, right? This is the shorter version, but. So rewrite this so the bases are the same. Do you agree that this is a 4 squared? But you can change the 16 to 4 squared. If it has a power on it, do you agree that that's going to be 2 times x? So we said if you have a power raised to another power, then you multiply. If I change the 16 to a 4 squared, I have a power to a power, they would just multiply together. Okay, so now they are the same. If they are the same, you can say that the powers are equal to each other. So that means that 2x is equal to 4. So x is equal to 2. Double check that. Oh, no, that's wrong. Oops. Yes, I said you set them equal to the powers. The power on this guy is a 1, right? I don't know where that 4 came from. So divide both sides by 2. The answer is 1/2. That makes sense. The procedure. Just match the bases if you can. So this was a 4, so change them to 4s. Set the powers equal to each other, solve for x. What is 1/2 power? That's the same as a square root, right? So it makes sense that if I square root 16, I get a 4. So it should be a 1/2 power. Anyway, any question on the algebra here? That's okay. You guys cool on this page? No questions? All right. So base E is just a number like pi. E is about what, 2.17, something like that. It's a very special number, but it's just a number. The goal is to match the bases and they're almost the same, they're almost ready. So e to the 6x minus 1 equal to e to the 4 to the x. So what do you do with these powers? Yeah, you have a power to another power. What's going to happen? We said you just multiply them 4 times x. Once they're the same, use your property that says you can set the powers equal to each other. See what I mean? At that point, just solve for x and you're done. Subtract 4x. Add 1. Divide by 2. This happens to be a half again. Just so happens. So the goal is to get the same bases, a to the b equal a to the c, so you can set b equal to c. That's what we're doing. That's it. You guys have any question on number 5? Does the algebra make sense? Do you see how we apply the property? Okay. You want to do one more of these, or now I'm going to move on to something else? This makes sense to you? It's all right. One more? Okay. We'll do a hard one.
Aw. Pretty. Can you go on?
Yeah, we're doing the next page. You guys cool on this page? This one looks weird. 27 to the 4x equals 2, 9 to the x plus 2. Solve for x. So the powers are up top. It's an exponential equation. Use the fact that if they have the same base, you can set the powers equal to each other. Change it to the same base first. You see anything in common with the bases? Should see something. Yeah. Yeah, something to do with threes, right? For sure. Yeah, 27 is 3 cubed. And what is 9? Yeah, 3 squared. So change them both to 3s. That way they'll have the same base. So change the 27 into 3 cubed. That makes sense? So now they have a power raised to another power, you have to multiply. So 3 times 4. 2 times all that, it's going to be. See how you got to multiply the entire thing. So that gets us to here. Because cool with that algebra. You see how we got to this step? Because that's the goal, is to get to here. Once you're here, you can apply this. Can you get here?
Out of the example, it is 9x plus 2, right? Or is that 9x minus 4?
Well, here? Yeah, that's a plus 2. X plus 2. So once you have the same basis, you can apply this. And we're back to beginning of the semester kind of question. Right? Solve for x. So subtract 2x. And then divide by 4. Yeah, I'm sorry, 10. Any questions about this process? It's not too bad. We're gonna move on to something else now. The end of the homework has interest problems. So I'm gonna give you, I think, 3 interest formulas. And then I'll let you work on your stuff. Simple interest. We'll call A future value. R would be rate. T will be time. It's always in years. So if the question does not give you years, you need to convert to years. For example, if you're given 6 months, you would say half a year. Okay, you wouldn't plug in 6. Does that make sense? And you must always use years for these formulas. If they give you months, you would like 6 months, you would say half a year. You don't plug in 6, you plug in 1/2. Okay, so keep that in mind. Always in years. Let's forget, it's the other principle. Number of times compounded per year is what n is. Okay. Simple interest is equal to A. A is equal to P times 1 plus R times T. Interest would simply be PRT. Compound interest. Yeah. So it should be no big deal, right?
This was like.
So when you compound the interest, they have to tell you how many times per year. So if they say monthly compounding or yearly, then n will be 12 or 1 or whatever. Okay. You could technically solve for P to create another formula. If they ask for principal, you could use this. Let's put a minus on the NT. You divide it out, you would solve for P. Don't know if that's going to come up, but there you go. You can also solve for Rn and etc., but I'm not going to do that for you. Now, if they say continuously compounded interest, you will use this formula. PERT. So P times E to the RT. And in real life, I don't think people use simple unless you're making a deal with somebody, you know what I mean? They agree to it. Compound is a little more common. I think nowadays, though, credit cards do continuous compounding because they want their money. That's why you always pay it off at the end of the month, right? And if you don't, they're gonna get you little by little.
Have any credit cards?
Hmm?
Do you have any credit cards?
Yeah, I do.
It's your part. And then we change them. They say consciously or continuously?
Continuously. There's an I right there.
Oh,
IN.
okay. No, it's conscious.
I'm sure it's conscious when they're trying to, while they're taking our money, right? They know what they're doing. Not an accident, right? All the allergy stuff. Well, that doesn't help. Right, find the future value and interest earned if $8,000 or $8,704.56 is invested for 9 years. At 4% compounding. Compounded semi-annually. So do part A. Well, wait a bit. A lot of stuff.
What is that? We have to, interest earned?
Interest earned if $8,704.56 is invested for 9 years at 4%. Hope you'd wait 9 years. It's not 4% is pretty good.
Saturday, 10. It was 10.
I think right now, the way the economy is, CDs are pretty decent. Surprisingly,
What is it?
CDs and saving accounts,
Oh, yeah.
they're the highest if they've ever been in a long time. Like I think I've been seeing like 5 or 6%. So it's for doing nothing, just putting your money in there for a few years.
Do you have any CDs?
No, not yet.
If you put it in, you can't get it out. Where is it?
Yeah, you promise to keep it there for X amount of years, and they promise to give you 4 or 5% back. when it's time. So it's a guaranteed money for doing nothing, but it takes money to make money.
Yeah.
So it's like, if you can't just ignore 10K for 5 years or
Yeah.
3 years, then that sucks, right? Life
You
sucks.
can't?
If you can, then it's really not for you, right? You have to wait till we have enough. Till you're ready,
So we were there for
whatever years.
10 stacks for 9 years.
Yeah, you invest money you don't need, right? You don't invest stuff that you need. If you need it, then it's not time to be investing.
Every time I go to the store, whenever.
So if they say compounding, you should be thinking this formula here. And we have to label what is everything. So they mentioned compounding semi-annually. So how many times per year is that? Is it 6?
No, yeah, one.
Semi means what? What does semi mean?
Every other?
Partial.
Be twice, right? Twice a year. Right?
What do you think?
You don't know what is, I guess you gotta Google, what does semi mean?
Lost your fucking feature, I'm asking you.
Yeah,
If I
there's,
did, if I didn't need to know, I wouldn't be here. Oh, yeah, so mine is, every 6 months,
yeah, so it would be done twice, right?
done twice. Ha.
Yes. What is the principle in this case?
Okay.
Principle is what you're putting in, what you're saving, investing, the money you started with.
87.4%. The rate is
What is the rate?
4%.
But we cannot use percent inside a formula. What is that as a decimal? Okay. How much time are we talking? N is the number of times compounded, and we all agreed twice a year. Is that everything? So now we can find out how much we'll have in the future, 9 years later. The future value would be P times 1 plus R over N to the NT. At this point, you need a scientific calculator. Or a graphing, one of those. 8704.56 times 1 plus 0.04 over 2 to the 2 times 9. You think it'd be a lot of money? Maybe not. So we will have in the future $12,432.
Total for the banks.
Yeah.
That's it.
We're doing nothing, yeah.
That's just a total.
That's the total,
That's a grand total.
grand total. So you put in 8704.
It's just $3,700. For 9 years.
9 years, so. What happens when you put in like 100K or 1 million, right?
That's crazy.
You see why it's, once you have a certain amount of money, you don't have
You
to.
should move that rate up.
Yeah, rates, the time variable, the rates are all have big impacts. Like if you're saving for retirement or like a mutual fund in the future, time is what matters most. Uh, But once you hit a certain amount of wealth, you can survive off, like, let's say you have like 10 million in the bank, right? Let's just pretend. So if you get 4% a year, because the average, based off the last 30 years, average return on investment is about 6%, 6 to 10. Yeah, so you would get about 400,000 every year if you only take 4%. So that would be your yearly salary based on your investment. So once you get a certain amount of money, it just keeps growing forever. But you don't need 400K a year to live. You could live at 1%. So you can let the other 5 or 6 or 7% just go back on the pile, keep growing. So in 10, 20 years, you're gonna have a giant pile and you're still good. So once you have money. What's that?
That was for 10 million.
If you have 10 mil in the bank, 1% would be about 100K a year. But it's projected to grow at least 5%, and that's like a low estimate. So we've been last 4 or 5 years, we've saw 10% growth on investments. So once you have a certain amount of money, you and your family will continue to have money forever because it'll just keep building. You can just keep living off interest. So it's nice. Depends what we're talking about. I'm talking about just return on investments, having stocks and bonds, etc. A portfolio. Savings accounts, CDs, etc. are about 5 to 6 right now.
Oh, but that's for 9 years.
Depends on the agreement.